All right, so here we go again. I hope you all had a good reading week. Thank you for the assignments. And then this looks like most people have picked things up, but that's just old stuff that hasn't been picked up, including assignment 3, which I have not returned before. Okay, so I don't know about you, but it's been a little while, so I needed a little refresher about the sort of things that we've been talking about. And so I've written a couple of pages of notes here ahead of time. All of this stuff is in notes that you have already, so you don't have to feel like you need to scramble to write any of this down. What we've been working on is trying to find the wave functions of the hydrogen atom, a light electron trapped by the potential of a heavy proton. So what we did is we said, well, let's assume that the proton doesn't move, and then we have this light electron moving around it. And we're going to choose the origin to be the location of the proton. And so R represents the distance between the proton and the electron, and then theta phi are these spherical angular variables. Um, we went ahead and tried to solve Schrodinger's time-independent equation using a separation of variables technique. We've actually finished the angular part. The angular part did not depend on the potential because we're assuming that we have a central potential, which just means that it's a potential that depends only on the magnitude of R, the distance between electron and proton. In our case, that central potential is the Coulomb potential. So it's just a 1 over R potential. Okay, and so I've written down the solution for the angular part that doesn't depend on R, and it was these so-called spherical harmonics. Just to give you a sense of where we're going, when we solved this angular part, the easiest part was the phi dependence. And so phi was just e to the minus m times phi, where m was some integer. The reason m had to be an integer is because we required that the potential, if I go from phi to phi plus 2 pi, I have to get the same answer back again. And so that's what quantized m. What we'll find, probably not today, but over the next couple of classes, is that this m, this quantized m, it's going to be associated with the z component of an angular momentum. That's the direction we're going. We also solved the theta part of the equation. That required more work. We had to write down this differential equation, and in principle, we would put a series expansion in there. We have to terminate the series expansion and all that stuff. That led to quantization of a parameter L. L is going to be some integer, 0, 1, 2, 3, and so on. As we go through the next couple of classes, what we're going to find is that this L is going to be associated with the total angular momentum. And there's a bit of this theme coming along. So when we have and impose boundary conditions on our parts of our wave function, that's what leads to quantization. And we are going to do today is we're going to see that putting boundary conditions on the radial part of our wave function is going to lead to quantization of energy. That's the same thing we saw with the quantum harmonic oscillator. So now we have these other parts, these angular parts are going to quantize angular momentum. Okay, so the radial equation we were working on, it was kind of a bit of a mess, and we had to do lots of kind of redefinitions or changes of variables. And so I've written down all these important ones. The top line is what we started with. And so the first thing we did is we defined some u as a scaled version of big R. We defined kappa in the usual way, minus 2me square root divided by h bar. We're thinking about the bound states of the electron trapped by the potential of the proton. That means the energy is negative. E is negative. That means this minus E is positive. So this kappa is a positive real quantity. Again, we kind of scaled this R to be rho is kappa times R. And so finally, U we defined in this funny way. What we did is we tried to pull out what we thought the asymptotic behavior of this solution to this differential equation was going to be. We looked at what would happen if we said our rho was very large, and we ended up getting this kind of exponential e to the minus rho dependence. We looked at what would happen for very small rho, and we got this kind of power law kind of thing. So what we did is we defined U in terms of a product of these asymptotic behaviors and some other function that we're going to try to find. And once we did that, when we put in these new variables into our original differential equation, this is what it boiled down to. And we finally got to the point where we're going to assume a power series solution. We threw that into our differential equation, and that led to a recursion relation between the coefficients in the power series. And that's essentially where we got to before the break. And so what I want to do is I want to finish this off. And what we'll see today is how we end up with this quantized energy for the hydrogen atom. So I just want to give a sense of how you would work with a recursion relation like this. So what you might do is you might say, okay, what if I took j equals 0 and threw it into our recursion relation for these coefficients of the power series? Well, j equals 0 on the left-hand side is going to give us a C1, and it's going to be equal to some stuff times C0. And so if I put in j equals 0, I get 2L plus 1 minus rho naught in the numerator. And then what do I have in the denominator? I have a j plus 1. It's going to become just a 1. And I have a 2L plus 2. So 2L plus 2. And so what we end up with is 1 minus rho 0 over 2L plus 1 C0. So I could keep going. I could say, well, what if I put j equals 1? Then on the left, I'm going to get a C2. Whoops. And that's going to be equal to, well, let's see. If I put in j equals 1, I get a L plus 2. So I get a 2L plus 2 minus rho 0. And then I get a 2. And let's see, I'm going to get a 3 plus 2L, I guess. So we're going to get a 2. Why do I have... I think I have something funny in my notes. Don't die. So this is going to be 2. This is going to be 1. So it's going to be a 1 plus 2L plus 2 times C1. But I already know C1 here, and I could take this expression and I could throw this in for C1. And so now I have C1 in terms of C0 and C2 in terms of C0. I could keep going and I could get C3 in terms of C2, but then I can use my C2 result and get C3 in terms of C0. So I could get all the coefficients in terms of just C0. So there's only one unknown, and the way we would get that last unknown coefficient is through normalization. So we can keep going in this matter and we can find all coefficients in terms of C0. And then we would need to find C0 using normalization. And we'll see how all that works eventually. Okay. So what I want to do is I want to see how are we going to get this energy quantized. And the approach is going to be to take this recursion relation and look at what happens if we take this J to be a very large number. So let's examine the recursion for large J. All right. So I want to get this thing on the screen if I can. All right, something like that. Okay, so we're going to take J to be so large that it's going to dominate a lot of these other quantities. So in the numerator, I'll say J is so large that I'm just going to ignore the plus L and the plus 1. And in fact, I'll also ignore the minus rho naught. And I can always just keep increasing J large enough until that's valid. And so we'll say Cj plus 1 is approximately, let's see, we'll have a 2j in the numerator. In the denominator, I have a j plus 1 and I have a j plus 2l plus 2. So what I'm going to do is I'm going to say, well, I will take j and then the j plus 1 and then the cj. Okay. Now what we could do is we can cancel a factor of j. If I wanted to, I could probably ignore the plus 1 as well, but I'm going to keep it in there just for convenience. And so this is approximately 2j plus 1 cj. All right, so that's the large J approximation. So I want to see how does this behave if we actually put in some values for J. So let's take J equal 99. So I'll get C100 is approximately, well, it's 2 over 99 plus 1. The reason I kept plus 1 in here is just because I wanted to get the 100 in the denominator. So I'll put 2 over 100, C99. All right, and then let's go to J98. Well, in that case, we'll get on the left, J plus 1 is C99. And then we'll get 2 over 99, C98. Okay, well, what does that mean? That means C98, if I solve for that, is 99 over 2, C99. But C99, I can solve for over here. It's 100 over 2, C100. And so that's going to be 99 over 2, 100 over 2, C100. And I could keep going in this manner, and I could write C97 would be this exact same thing, but then I'd get a 98 over 2. And then if I keep going, I get a 97 over 2 and a 96 over 2, and so on. So you continue in this way, and you would say C0 is, to a rough approximation, well, what is it? 100 times 99 times 98 times 97 times 96. That's the factorial. So it's J factorial. And then what I have, 2 times 2 times 2 times 2 times 2, J times. So that's 2 to the J. And then it's Cj. Or Cj is 2 to the J over J factorial, C0. Okay, so that's what I want to work with. And I want to see, what does that mean for our power series solution if I put in the coefficients that look like that? Okay, so if this were the case, then let's see, this V rho was the sum of Cj rho to the J. Well, that would look like we'd get our C0, and then we'd have the sum of 2 to the j over j factorial rho to the j. But the 2 to the j and the rho to the j, I can combine those things. And so this would be C0 sum over j of, let's see, 2 rho to the j over j factorial. Does anyone, what does this look like? What is, yeah, I think I heard it already. What's the sum of x to the j over j factorial? Taylor series for yeah, that's right. So our x here is 2 rho, and so this is like C0 e to the 2 rho. All right. Well, if we go back, and the reason I wrote out this long summary is because I want to use part of it. So our solution for R is determined by this U thing. And the U is going to have rho L plus 1, e to the minus rho, and then here's our V, which we've just written as that power series, and we showed that's that exponential. To actually get to the radial part of our wave function, I'd have to take this and I'd have to multiply by R. That's sort of similar to multiplying by rho. Okay, so let's just recall that, let's see, U to the rho is equal to rho L plus 1 e to the minus rho V to the rho. Okay, so that's going to be rho L plus 1 e to the minus rho C0 e to the 2 rho. Now, there's a point made just at the end of the last class is that this V certainly diverges as rho or R gets large. But what really matters is how does the radial part of our wave function behave? Well, I have an e to the minus rho. It's only going to partially cancel the e to the 2 rho here. And so this is going to be like C naught rho to the L plus 1 e to the rho. Even if I multiply by r to get back to the radial part, the exponential dominates the behavior. So I don't care about that power out front, that power of rho. So as r or rho goes to infinity, the u of rho and r of r would diverge, which means that r of r is not normalizable in this case. And so that means that I can't allow this recursion relation to go on forever. We have to truncate it. We have to kill it at some point. And the way that we're going to kill it is we're going to make the numerator go to 0 for some value of j. And if we can do that, we can find some cj plus 1 where all the coefficients at j plus 1 and higher are 0, and only the ones at j and below are non-zero. Okay, so that's the plan. So to avoid divergences, we require this recursion relation, which labeled in a funny way, to be truncated. And in fact, let me write it out so that we have it in front of us. So it's j plus L plus 1 minus rho 0 is the numerator. That's going to be the important part for us. And then we have a denominator 2L plus 2 and Cj. Okay. So we pick some n such that Cn is going to be 0, but Cn minus 1 is not equal to 0. You can see if I make Cn equal to 0, like let's say j equals n, then Cn plus 1 is also equal to 0. But if Cn plus 1 is equal to 0, that means coefficients are going to vanish. Okay, so we set n equal to j plus 1 and force the numerator equal to 0. Okay, so let's give it a try. We'll have 2. And then I said we're going to try j plus 1. We're going to set that equal to n. So we're going to have n plus L. So the j plus 1 is contained in the n. And then we have to minus this rho naught. And we want that to be equal to 0. And so we say, therefore, I'm going to define this small little n. That small little n is going to be the sum of big N and L equals rho 0, where little n is equal to big N plus L. Now, clearly, big N is an integer because it's just j plus 1, and j is just an integer subscript for the different coefficients of the different powers of rho. L we found to be integer already when we solved the angular part to find the spherical harmonics. So if big N and L are both integer, then so is little n. Okay, both big N and L are integer. Therefore, little n is also integer. So since this power series that we've been working with, Cj rho to the j for our V polynomial, if n is j plus 1, then n can't go negative for sure, because that doesn't make any sense, because j starts from 0. So there's a restriction on the values that n can take on. We require n greater than or equal to 1. So recall n was equal to j plus 1. Okay, so if I say j equals 0, smallest possible value, then n is at least 1. Okay, and so what we're going to find then is that the ground state of the hydrogen atom will be n equals 1, L equals 0, and little n was n plus L would be 1. And we will find the ground state wave function of the hydrogen atom today. I think, pretty sure. Okay, so let's now actually quantize the energy. So remember that we defined a rho 0 a long time ago. I wonder if it's actually in here. Let's see, did I write it down? No, I didn't. But there was a whole bunch of constants in here from the potential. And that's where our rho 0 was defined. Let me remind you what it was. So rho 0 was me, the mass of the electron, times E times E. So that's the product of the electron charge and the proton charge from Coulomb's potential. And then there was a 2 pi epsilon naught. That's also from the Coulomb constant. It was Coulomb's constant is 1 over 4 pi epsilon naught. And then there was an h bar squared and kappa. Kappa, remember, was minus 2m times the energy all square root divided by h bar. So that's where the energy is going to enter in. So this is going to be m squared over, I'm going to move this, I'm going to run out of space. 2 pi epsilon naught h bar squared. So I've written down this thing exactly, and now we'll put in the 1 over kappa. It was h bar minus 2me times p. Okay, good. All right. So did we write it down? There it is. So now what we're going to do is we're going to say that rho 0 has to be equal to 2 times little n. And little n is an integer. And it starts from 1. Okay. But we said this was 2n. I want to find the energy. So what I'm going to do is I'm going to square everything to get rid of that square root. So therefore, let's see. 4n squared is going to be equal to, let's see. I would get me squared, but then when I get rid of the square root, I have an me in the denominator. So I cancel one factor of me. Then we'll get e to the 4th divided by 4 pi squared epsilon naught squared h bar squared. So this would become h bar to the 4th, but then this is an h bar squared, so we get h bar squared in the denominator. And then we have a 1 over minus 2e. I'm going to put a little subscript n on here because now this energy is going to depend on the value of this integer, little n. So therefore, en is equal to, so all I do is multiply over here, divide by the 4n squared, and what do we get? We get minus me e to the 4th. Let's see, 4 times 4 is 16, times 2 is 32. So 32 pi squared, epsilon naught squared, h bar squared, and then there's a 1 over n squared left. These are all just fundamental constants or properties of the electron. All those values are known. If you put them in, this comes out to be what you probably already know, is the minus 13.6 in units of electron volts divided by n squared. And this is Bohr's famous formula. And he came up with this in 1913, which predates the Schrodinger equation. So he worked this out without having Schrodinger's equation and solving the differential equation like we've done. And so this is quantization of the hydrogen atom energy spectrum. Okay, I want to define a couple other things that will be convenient for later. So rho naught was 2n. We've already used that. And we know that rho naught is me squared over 2 pi epsilon naught h bar squared kappa. Okay. So if you put 2n here, what I want to do is I just want to solve for kappa. All right. So kappa is me squared. Let's see. We have a 2n here. So the 2 pi times the 2 becomes a 4 pi. So we get a 4 pi epsilon naught h bar squared. And then we multiply by kappa, divide by 2n, we get a 1 over n here. All of these constants inside the brackets, they have units of distance, position, or length. Let's say length is best. So all of this is defined as A. And this is the Bohr radius. And so we could write kappa as A over N. All right. So finally, let's recall that we're kind of undoing all these changes of variables that we did in order to solve the differential equation. One of them was that rho was defined to be kappa r, and so therefore rho is equal to kappa is 4 radius divided by n times r. So it is r over sorry, what have I done here? Sorry, I made a mistake. Let me fix it. These things in the brackets is the inverse of the Bohr radius. And so kappa is 1 over A times N. And so that means rho is R divided by A times N. Okay, good. All right. So let's then figure out the actual radial solution to our wave function. All right. So it was going to be a rho L plus 1 times e to the minus rho times v of rho. This was not the complete r. This was our u. And then r we got by multiplying u by 1 over r. So that's our radial wave function. And so we could start putting stuff in. Rho we'll put in like this, and it'll just go in wherever we see our rhos. So where v of rho is our power series. That's not right. This is going to be a subscript, superscript. And we now have a way of calculating these coefficients. These coefficients are Cj plus 1 is 2, J plus L plus 1. We used to have a closed bracket minus rho 0, but rho 0 is 2n, so I can put a minus n in here and factor out the 2. And then we have j plus 1, j plus 2, L plus 2 times Cj, where I've used rho naught is equal to 2n. All right. And so this is in principle our solution for the radial part. It is messy, I agree, but it is the solution. N equals 1, 2, 3, and so on. Okay, and you can see now how these n's, the value of n is going to truncate the recursion relation of the coefficient. I put in some integer here, some negative n in here. J is integer, L is integer, and so some combination of these is eventually going to make the numerator 0. At that point, all the higher J coefficients will vanish to 0. All right. So I just want to make some kind of general notes about summarizing what we've done and sort of have like a mental picture of what we've been talking about. And then I think what we'll do is we'll actually write down some, well, at least the ground state wave function for the radial part. So let's do that. Let's recall that we're considering the bound states of the hydrogen atom. The electron is, if you like, in some sense, confined by the effective potential of the proton. And the way we got bound states was to require E be less than 0, which is why we have found that En is minus 13.6 electron volts over n squared. I can put in any value for n here, and I always get a negative energy consistent with this idea that bound states have negative energy. Okay, so what would it mean then if the electron energy became positive? Well, what it would mean is that it would be no longer bounded by the hydrogen atom. It still would interact with the proton or the nucleus, but it would be a scattering state. We'd have some high energy electron come in. It would have some electrostatic, if you like, interaction with the proton that would deflect its path, but then off it would go, never to come back again. So it would scatter off of this proton rather than be in a kind of, if you like, fixed orbit, if you like, around that proton. Okay, the other thing that I wanted to point out is that whenever a quantum particle is confined, and it's easiest to think of the infinite square well, where we have these rigid, hard boundaries where the wave function had to vanish. Think about that. We confine an electron, which maybe has some de Broglie wavelength, if you like, or some wave function. And then that wave function has to vanish at these infinite potential walls. Well, what that means is we can only have standing wave patterns fitting inside the well, and the width of the well determines the wavelengths that are allowed. And those allowed wavelengths are what determine the quantized energy values. And so we have something similar here with the hydrogen atom. We don't have infinite potentials with like hard boundaries, but we still are confining the electron. And that's exactly what led to conditions on the wave function, the boundary conditions that led to this quantization. Okay, so whenever a particle is confined, we place boundary conditions on its wave function, which leads to I don't know, how do I want to say it? Which leads to restrictions on the allowed energies. This quantization is not really that special to quantum systems. You think of a guitar string, we force the position of the string to be, say, 0 at the two ends of the guitar, and then we pluck it, and all that we're allowed to have are standing waves. And so we get fixed frequencies for the string that we play. So it's that kind of idea. Also, this idea of bound states and scattering states is also not restricted to quantum systems. I won't write it down, but if you think of the Earth, we're in an orbit around the sun. We're bounded by the gravitational potential of the sun. And that's it. We're not going anywhere except in this orbit. But you could have a very high energy asteroid comes through our solar system, and it's going to be deflected by the gravitational interaction with the sun, but its trajectory will be deflected and it'll just move away and never to return. Okay, so hydrogen's ground state. How are we doing time-wise? Okay, not bad. Is n equals 1. So n equals 1 gives us the largest negative energy. So that's the lowest energy state. And I'm going to take L equals 0. Okay, so from Cj plus 1 equals 2j plus L plus 1 minus n over j plus 1, j plus 2L plus 2 Cj. So there's our recursion relation. We're going to start to try to build this ground state wave function. All right, so let's try j equals 0, n equals 1, L equals 0. Okay, so C1 is going to be equal to 2. 0, 0 plus 1 minus 1 is going to be 0 in the numerator. Plus 1 minus 1. And then the denominator doesn't really matter, but we get 1 plus 2, C0. But this is just equal to 0. So right away, we see C1 is equal to 0. So if I put in j equals 1, I'd get C2 here, C1. C1 is 0, so C2 is 0. C2 is 0, so C3 is 0, and so on and so on. So we have only one surviving coefficient in this case. And so we say, therefore, V of rho, which is our power series, is just C0, and that's it. Nothing else. Rho, we said, was R over N times A, where A was that Bohr radius. But if N equals 1, then this is just R over A. Okay, so for N equals 1. All right. Well, therefore, R10. So N equals 1, L equals 0 is equal to. Well, I think we wrote it down, didn't we? There it is. So we'll have a 1 over R. We'll have rho to the power 1, e to the minus rho, and then our power series, but our power series just reduced to just C0, a constant. So we'll put all that stuff in. So there's a 1 over R. There's a rho to the L plus 1. So it's rho to the 1, e to the minus rho. And then our power series is just a C0 in this case. Okay, so it's C0 over R. Rho is R over A. So this is R over A. E to the minus R over A. And I guess that's it. Even these R's cancel. And so our R10 is equal to C0 over A, e to the minus R over A. All right. Now, if we want to construct the full wave function, we're going to need to know the C0 coefficient. And to do that, we've used normalization. So we're going to use normalization to find C0. And the normalization condition is R goes from 0 to infinity. And it's going to be R and L squared. And then in spherical coordinates, we have R squared dr for the radial part. Okay, so therefore, if we do this for our ground state, it's going to be R10 squared. Notice, really, I guess, if you like, I should have did the absolute square of this thing, but we can see that A is some Bohr radius. It's just a bunch of constants. It's real. R is real. So there are no complex quantities in here. But I guess to be perfectly safe, we can put in an absolute square. So let's do that to be proper. R squared dr. All right. So let's see, where did our, there it is. So we'll get a C0 squared over A squared, the integral from R equals 0 to infinity, e to the minus R over A, R squared dr. So that's what we have to work out. I'm going to make a substitution. X equals R over A, so that dx is 1 over A dr. So therefore, and okay, we want this all to be equal to 1 if it's normalized. So 1 is equal to C0 squared over A squared. Let's see. It's going to be the integral from 0 to infinity of e to the minus x, and then we're going to have a dx. The r squared is going to give us a factor of a squared, and the dr is going to give us another factor of a. So we're going to pick up an a cubed in here. So I think we get an a cubed, and I think we get an x squared. Okay. So hopefully that's sorry, what did I do wrong? I have I made a mistake. Does anyone see what my mistake is? Here, I'll show. It's in the exponential. What didn't I do? We had to square this thing, right? So we got a C0 squared and an A squared. I didn't square the exponential. So let's fix that. I need a -2 here. And then my substitution, I'd have a 2 here. And I would have a 2 here. And we're going to pick up here. From the r squared, we're going to get an a over 2 squared. From the dr, we're going to get an a over 2. So overall, we have an a over 2 cubed. All right, so that's better. Okay. So we end up with C0 squared times a over 8. And the integral from 0 to infinity of x squared e to the minus x dx. Now, I'm not going to prove it, but there's a beautiful way to just know what this integral is going to be. The way you would solve this integral is you just do integration by parts 2 times. The first time, it's going to change the x squared to an x. The second time, it's going to change the x to a 1. I guess it will, the first time it'll be x squared will go to a 2x. And then next time we'll just get a 1. And you can see I get 2 and then times 1. What if this was x to the n? Then I'd integrate by parts n times. The first time I'll get a factor of n coming down. The next time n minus 1, the next time n minus 2, the next time n minus 3. And you can see there's going to be like an n factorial that arises. Now, you might worry that, well, integration by parts, I also have this uv evaluated between the limits. Well, uv is always going to involve x and e to the minus x. So when I put in the 0 integration limit, the x is going to make it 0. When I put in the infinity integration limit, e to the minus x is going to make it 0. So that's all going to vanish. And it turns out that integrals of the form. Now, it's important that this only works when we integrate from 0 to infinity. So if you had some different integration limits, then you're out of luck. But this integral is just equal to n factorial. And so for us, Rn is equal to 2. And so what we have here is this is just 2 factorial which is just a 2. Okay, and so therefore we get 1 is equal to C0 squared. 8 divided by 2 is a 4. And so therefore C0 is equal to, let's see, 2 over root A. And so that's our normalization for the ground state, the radial part of the wave function. And we can put that into this expression here. So we'll get a 2 over square root of A. And so that A will become A to the 3 halves in the denominator. And so therefore, R10 is equal to A to the 3 halves, E to the minus R over A. One thing I just want to highlight before we continue is that the total wave function is going to be the product of this radial part and the spherical harmonics. The spherical harmonics have no units, right? Everything is just in radians. And so the units of the wave function are determined solely by this radial part, and it has an A, units of length, to the 3 halves in the denominator. That makes sense because we require the square of our wave function integrated over all space, over all of R3, let's say, has to be a probability unitless. And so if I square it, I get 1 over length cubed. But then when I integrate over all space, I get that length cubed in the numerator, and those cancel, and we get a unitless thing. So this, we can see, has the correct units. Okay, so we also know that for our spherical harmonics, the y00 was actually pretty straightforward, pretty simple. It's just a constant. It was 1 over root 4 pi. So then we can finally write down the ground state of the hydrogen atom. And it is given by the radial part multiplied by the angular part, like so. And if we combine these things, let's see, the root 4 is going to cancel with that 2. And we just get a 1 over the square root of pi a cubed e to the minus r over a. And look at that. A nice, beautiful, simple expression after grinding out days of algebra solving differential equations. So this is an achievement. This we should feel good about. There it is. Okay, now if I wanted to get an excited state, I would put in n equals 2 instead of n equals 1. So if we wanted the n equals 2 state, we need to first pick the value of L. And so L could be equal to -1, 0, or +1. Okay, so, and then return to our recursion relation. So let's just do a little of an example. We won't do the whole thing, but we'll just see how this works. So suppose we wanted the state for n equals 2 and L equals 0. Then we would go to our recursion relation. I'm just going to write it out yet again, just so it's in front of us. So j plus 1, j plus 2L plus 2, and then we have our Cj here. Okay, so we start in the normal way. We go, okay, j equals 0 will give us C1. Now we have to be a little careful because it's different now. Now we have to put in j equals 2. So we're going to get, this is going to be 2 times 2 plus, sorry, what am I doing? The 2 is going to go in here. That's what I wanted to say. All right. So we get a j equals 0. So we get a 0 plus 0 plus 1 minus 2. So this is j equals 0, L equals 0, N equals 2. So this is going to be 1 times 2 in the denominator. So 1 times 2. And let's see. This 2 is going to cancel with that 2. And we just get 1 minus 1, which is minus 1. And so we get, sorry, I forgot. I need a C0 here. So minus C0. All right. Now, previously we found C1 was equal to 0. This time it's not equal to 0. So we have to keep going. We go to the j equals 1 state. That would tell us what C2 is going to be equal to. It's going to be 2, and then j equals 1 plus L equals 0 plus 1 minus 2. Okay, so we can already see that. So this is 3. This is going to be C1. We can already see that the numerator, 1 plus 1 minus 2, is going to be 0. And so this is 0. And that means that our V power series is going to be C0 plus C1 times rho, but C1 is minus C0. So we get a minus C0 times rho, which is C0, 1 minus rho. Okay, and so then we could say, well, therefore, R20 of R is going to be E, 1 over R, rho, e to the minus rho, and then our V power series is C0 minus rho, C0 times 1 minus rho, and rho is equal to R over N times A, N equals 2. So we have R over 2A. Okay, and so if you put that in and work it all out, you find that R20 is going to be C0 over 2A, 1 minus R over 2A, e to the minus R over 2A. And then I'm not going to do it, but you would have to normalize. And in fact, the normalization is not going to be difficult if you use our factorial trick. Because you can see it. If I square this out, I'm going to have e to the minus R over A kind of thing. That's totally fine. I'm going to have this thing squared. So that's going to be some polynomial in R up to R squared. I'm going to multiply by R squared dr. So that's going to make my polynomial go from R squared to R to the 4th. But every single term in that polynomial, we could evaluate using our factorial trick. And so they're not hard to do, although I'm not going to do it. So we have to normalize again to find C0 and go on and on and on. Okay. That, I think, is the easiest way to build up these radial parts of the wave functions, and then you just multiply them by the spherical harmonics that we already know. All right. There's another way to do this, and so I'll tell you what it is. In general, this power series, V of rho, it's written in terms of a special function. And just like our spherical harmonics involved these associated Legendre functions, our radial function is going to involve some other special functions. So it's denoted L with these subscripts that depend on the values of N and L, where this thing is equal to -1 to the P. The Pth derivative. I don't know if I've ever said Pth before. Pth derivative of some other special function. This L thing is called the associated Laguerre polynomial. I don't know, it seems like a lot of French people were working on these polynomials. We're talking Legendre, Laguerre, Hermite, they all sound French to me, but I could be wrong. And so notice that to get the associated polynomial, we have to take derivatives of some other special function. So this LQ is e to the x over q factorial d by dx, the qth derivative of e to the minus x, x to the q. And this is the Laguerre polynomial. So if you actually wanted to do this, what you would first have to do is you pick your N and your L, and you go and figure out, okay, Q is going to be N minus L minus 1. And once I have that, I go here and evaluate the Qth derivative of this thing, and that gives me my polynomial. Then I take that polynomial and I stick it in here, and I have to take the Pth derivative of that. It will give us the exact same answer that we found just working through our recursion relation. So I'm sure you wouldn't be surprised to hear that these things have all been worked out, and so people have written down general expressions for the hydrogen atom wave function. So the hydrogen atom wave function. All right. So it's going to depend on three numbers, N, L, and M. L and M, we first got them from the angular part, the spherical harmonics. N, and in fact, L, play a role in the radial part. So what it looks like, it's a bit of a beast. So 2 over NA cubed, N minus L minus 1 factorial 2n n to the minus r over NA, and then it's 2r NA to the L. And there's the associated Laguerre polynomial, 2L plus 1. Okay, and then we still have to multiply by the spherical harmonics. So there it is. This is the normalization factor for general N and L. We did it for the one-off case of the ground state, but people have worked it out in general. Let me just, so it's all in one place, I'm going to write down the spherical harmonics again. It had its own monster of a normalization factor. Okay, and then it was e to the im by. So the quantization of m was requiring e to the im phi and e to the im phi plus 2 pi being equal. And then we have our associated Legendre functions. Okay, so that's the big solution. We did it. We worked through it all. Let's see if I can make this box here. Yep. All right, good. Okay, good. And you can confirm if you want to that the hydrogen wave functions are orthonormal. So if we were to, I should be a little careful here. Let me put primes on these things. So if we were to take the inner product between psi n l m and psi n prime l prime n prime, integrate over all space in spherical coordinates, we would find that this would be non-zero only. Well, in fact, it'll be 1 only if n is equal to n prime, L is equal to L prime, and M is equal to N prime. Okay. So we have like today's class is close to finish. So we have, I think, 5 more classes left. And what we're going to do in those 5 classes is we're going to talk about angular momentum and how they relate to these L and M values. And so what I want to do is I just want to start laying some of the groundwork for this angular momentum in the next, I don't know, 8 minutes or so. So we are in section 4.3, angular momentum. And so it'll be a bit of a shifting gears. So we're going to move away from solving big differential equations and into playing with a bunch of commutator relations, which is kind of fun. All right, so the stationary states of hydrogen have 3 quantum numbers. Those are n, l, and m. So n was from the radial equation. L we got from the theta part of the angular equation. Theta of the angular equation. And then m is from phi of the angular equation. This n is quantization of energy. We will show that the L is quantization of total angular momentum. And this M is quantization of the Z component of angular momentum. So clearly, we have not shown these last 2 yet, but that's just the direction that we're headed. Okay, so let's see, how are we going to attack angular momentum? Let's start just with classically reminding ourselves of how we would calculate angular momentum. It's the cross product between a position vector and momentum. Okay, now what we already know in quantum mechanics is that the momentum we can represent as an operator, and all we're going to do is put in our operators for quantum momentum and see what happens. So let's stick first with the classical case, just to begin. The way that I would calculate this cross product is I would write down a 3x3 matrix and take the determinant. And if you did that, the x component would be y pz minus z py. This is clearly in Cartesian coordinates. Ly would involve x and z. So it's going to be z px minus x pz. Lz is going to involve x and y. It's going to be x py minus y px. Okay, so in quantum mechanics, px is minus I h bar d by dx. Generalizing to 3 dimensions, py would be minus I h bar d by dy. And pz would be minus I h bar d by dz. Okay. So let's consider the commutator between Lx and Ly. And let's see what happens. The reason we're doing this is because we showed in the last chapter, chapter 3, the generalized uncertainty principle. It said if two operators commute, so their commutator equals 0, then we can know both those quantities simultaneously with arbitrary precision. If they don't commute, if this is non-zero, then that leads to some uncertainty relationship between these two variables. And what that means is if I know one of them very well, I know absolutely nothing about the other. So let's see what happens if we do this Lx and Lz. So y, pz, z, py, z, px, x, pz. Okay, so this is just Lx and this is Ly. So what we can do with commutators, this is, I can break this up into a bunch of individual commutators. So it's going to be ypz with zpx, for example. So there would be a ypz, zpx. And there would be a minus ypz, xpz. Okay, so y, pz, x, pz. And let's see, there's going to be another minus. There'd be z, py, z, px. Z, py, z, px. Then there's going to be a plus. So the minus and the minus is a plus. So it's z, py, x, pz. All right. Z, py, x, pz. Okay. Now, are there any of these that are obviously going to be 0? There's 4. Like there's the first one, there's a middle 2, and then there's a last one. Which ones do you think will vanish? Second one will vanish. Exactly, it will, because pz is going to be derivatives with respect to z. But I don't got no z's here. So there's not going to be any issues with moving x and before or after pz or y before or after pz. So this one will vanish for sure. Any others? The third one. This is going to be a derivative with y. This is going to be a derivative with respect to x. But this is z. There is no x or y in here. And so this will have no trouble. The other two we'll have to think about more carefully. Here's a z derivative, and there's a z. So that could be a problem. Here's a z derivative, and there's a z. And so that's going to be a problem. We don't have time to do it right now, but what we'll do on Wednesday is we'll start thinking about these two commutators and seeing what happens. What is going to happen is that we're going to find that, in fact, this commutator is not equal to 0. And that means I'm not going to be able to simultaneously know the x and y components of the angular momentum. Okay, so that's going to be one of the consequences. And then we're going to explore the properties of angular momentum in that way. All right, thank you very much. And we'll see you on Wednesday.